All right. Special stress states. Now, remember what we did last week. Last week, we discussed a bit about the rotation of the infinitesimal element. Once you find the most stressed point on a section, it is first you find the most stressed section, looking at the bending moment, shear force diagrams, so on and so forth. So the internal load diagrams. Then on that most stressed section, you can identify the most stressed point. Now, the most stressed point, you can also visualize it on an infinitesimal. All the stress is acting at that point. Now, that thing contains at least 3 numbers, sigma x, sigma y, tau xy. Okay, that's for a plain stress state. If it's a 3D stress state, it's more complicated. But for a 2D stress state, you have 3 numbers. Now, the problem that we face is that these 3 numbers are different depending on the reference system that you used. Because if you change reference system, those 3 numbers change. That's not good, because we want to talk the same language with all other engineers worldwide. But we can find a certain stress state. So for a certain rotation of the infinitesimal, there is always a certain angle for which the infinitesimal feels no shear stress. That kind of rotation, that infinitesimal there, is said to be in a principal stress state. Because in that state, this one here, this state here, there is no shear stress, and the direct stresses, the normal stresses, are the largest one and the smallest one. So the largest one, sigma 1, and the smallest one, sigma 2. Conversely, you can also rotate the infinitesimal element until you get to this condition here. It's called maximum shear stress state. So you can rotate it until you reach the largest possible shear stress. This doesn't mean that there are no normal stresses. Okay? So this one, for largest normal stress, you have no shear stresses. For largest shear stress, you will have all equal stresses. See, this is sigma average. All equal stresses all around, and there will be some residual normal stress. And this can be made clear by looking at Moore's circle. So this is what we did last time, basically. So I put here how you draw the Moore's circle, draw the axes, find the point A, find point B, connect them using a diametral line. So you locate the center here, that must be here because the tau is the same for clockwise and counterclockwise. So there is a symmetry axis on the sigma axis. So the center is always on the sigma axis, and then you can draw the circle. Once you know the center at point A, you point your compass here and draw the circle all around. Very easy. Close this. Looking at this, so this A and B represent the stress state on the infinitesimal. So this is the infinitesimal. So this is sigma x. In this case, sigma x for point A is negative and sigma y is positive. And the shear stress is like this. So this infinitesimal here is represented by this point A and this point B. Point A is sigma x tau xy, and point B is sigma y tau yx. Okay? So sigma x tau xy intercept point A, sigma y tau yx intercept point B. You draw the line, find the center intersecting the sigma axis, then you draw the circle. Once you've drawn the circle, you have all possible stress states. They all belong to the circumference. Now, this particular stress state belongs to this and this. But if I rotate this line, which is at 0 degrees right now, if I rotate this in this direction or in this direction, I can find the 2 special stress states. The first one is principal stress state. So if I rotate this line until I reach the horizontal on the sigma axis, I find that the largest possible normal stress is here, and the minimum possible normal stress is here. I call these sigma 1 and sigma 2. And as you can see on this line, tau xy is 0. See, on this line, tau xy is this, and tau yx is this, which is, of course, are the same. On this line, horizontal line, tau is 0. There is no tau. And that's exactly what I'm saying here. There is the largest sigma 1, which is in tension on the positive sigma. The smallest sigma 2, in this case, is in compression. And then there is no shear stress whatsoever. Always. You can always find an horizontal line, so you can always find this stress state. If I rotate this onto a vertical line instead, passing through the center, of course, what I have is the largest possible tau max, which of course, since this is symmetric around sigma, it occurs both at the top and bottom, tau max. One is clockwise, one is counterclockwise. And as you can see, this one, this center here is not at the origin. So sigma is non-zero. Okay? Sigma is 0 here, but the center is here. So for this line, you have tau max, but you also have an average stress. Why am I calling it average stress? Because, well, if you look at the center position is sigma 1 plus sigma 2 divided by 2. Okay? That's the average stress. And you can also find out that the average stress is also sigma x plus sigma y divided by 2. So it's the same for every, also sigma y plus sigma x divided by 2 also gives the center. So it doesn't matter where you are. Sigma x plus sigma y divided by 2, no matter which one is x and y, is always the average stress, always locates the center. All right. Another thing that we can find out from Moore's circle is that this radius here, from the center to B or from the center to A, doesn't matter, also this one, it's also a radius, is equal to this beast here. So the radius of the Moore's circle is always tau max. You do agree with me that this is a radius? And so this is also tau max. This is also a radius, so this is also tau max. So sigma 1 is not a radius, see, because the radius here is this. So sigma 1 is the average stress. So from the center, you add the radius. Sigma 2 is from the center, you remove the radius. Okay, so this makes complete sense. So you only need this formula. You only need this formula. Sigma average is here. Tau max is here. Sigma 1 is sigma average plus tau max. Sigma 2 is sigma average minus tau max. All right? All right. Let's look at the directions. So this is 2 theta p, 2 theta s. How much I have to rotate this line, but by how many degrees I have to rotate this line in order to reach sigma 1? So how much I have to rotate the infinitesimal in order to reach this special stress state? Well, I told you that this is the radius. This thing is this radius here. But this thing is also something squared plus something squared under square root. So this looks to me very much like a triangle. This triangle here. You agree with me? Well, this triangle here has tau xy as the first edge. This edge is sigma x minus sigma y divided by 2. Okay? So how much is this angle? 2 theta p? Opposite over adjacent. Opposite, tau xy, over adjacent, sigma x minus sigma y divided by 2, which goes at the numerator. Okay? So these things here don't come out from thin air. They are you can find them out. And of course, 2 theta s, what is it? It's the complementary angle, because 2 theta p plus 2 theta s gives you 90 degrees. Do you agree? So it's just instead of being opposite over adjacent, it's adjacent over opposite with a negative sign, because it must go in the opposite direction. So instead of being counterclockwise, it's clockwise. So it's the inverse of this with a minus sign on top. All right, that's it. All right. So let me remove this one. No, no, no. There we go. And now, failure criteria. Now, the problem is, look at this element here. Let me draw this nicely. What we know is that materials fail for certain stress conditions. The problem is, I can test the material by having a tensile test. Okay, so I take a tensile test on a material and I say that the yield stress is this much. Say the yield stress is 200 megapascal. But that's a number, one number. Here, I have 3 numbers. I have sigma x, sigma y, and tau xy. Which one of these must be greater than 200 in order for this to fail? This is a complicated question, because you want to compare 3 numbers to one number and say, if a certain condition is met and it's greater than this number, then it fails. But you can't compare a number, well, 3 numbers with one number, okay? So you need what we engineers, well, mathematicians really, call the crisis function. The crisis function is a function, of course, so it takes inputs and outputs. It takes 3 inputs and it spits out 1 output. So it's basically a meat grinder for numbers. Okay, you put everything in the meat grinder and then you come out with a single number. Now, there are various kinds of crisis functions. The 3 most popular ones are the Rankine, Tresca, and von Mises ones. Okay? These are also called failure criteria. But in reality, what Rankine, Tresca, and von Mises saying is that you can take these 3 numbers and I can give you an equivalent sigma. Okay, so I take sigma x, sigma y, tau xy, and I spit out sigma equivalent. The 3 inputs are sigma x, sigma y, tau xy. Okay. In fact, look at this. Rankine says the sigma equivalent is also called maximum principal stress theory, because the equivalent sigma is equal to the largest of sigma 1 and sigma 2 in absolute value. Okay, so you take the largest between sigma 1 and sigma 2, and then you spit out the equivalent sigma. And then this equivalent sigma must be smaller than the allowable stress. If this is smaller, the structure is safe. This is greater, the structure has failed. Of course, this one is only really applicable for brittle materials. So we don't take the yield stress, because brittle materials don't yield. Brittle materials, they just break, they fail suddenly. So you take the failure stress, ultimate tensile stress of the brittle material, and that's it. All right. But this is sigma 1 and sigma 2. I told you that in input I need sigma x, sigma y, and tau xy. It doesn't look like we have them here. Well, they are inside sigma 1 and sigma 2. Remember, sigma 1 and sigma 2 are made of sigma x, sigma y, and tau xy. So the effect is that this function is taking sigma x, sigma y, tau xy, and spits out sigma equivalent. That it's a single number that you can compare with the yield stress or the failure stress of the material. Let's look at the Tresca. Tresca is maximum shear stress. It doesn't look like we have shear stress at all here. Why? Well, maximum shear stress, if you have maximum, what is the maximum shear stress if I take a uniaxial stress? Let's say I have only this, sigma x. If I only have this, what is the largest shear stress? Well, let's look at sigma 1 and sigma 2. This becomes sigma x divided by 2 plus sigma x divided by 2. Sorry, we're looking at the largest shear stress. So tau max is this. Okay, tau max is this. So this is sigma x squared divided by 4 plus 0. The square root of sigma x squared divided by 4 is sigma x divided by 2. Okay, that's it. So tau max, for this thing, tau max is sigma x divided by 2. And so that means that sigma yield is also tau yield divided by 2. So that divided by 2 can go away, and you are left with this. So you take the largest. Remember, what is the radius? This radius here can also be seen as sigma 1 minus sigma 2 divided by 2. Sigma 1 minus sigma 2 is the diameter, divided by 2 is the radius, which is tau max. That's what I'm saying here. I've used sigma 3 here, and I put a couple of exclamation marks. Why? Because even on 2D stress, you always have 3 principal stresses: sigma 1, sigma 2, sigma 3, and they are in order. So if sigma 1 is positive and sigma 2 is positive, sigma 3 is 0. You have to look at the infinitesimal like a cube always. So you have 3 principal stresses. Okay? So if sigma 1 is positive and sigma 2 is positive, sigma 3 is 0. Tresca says the largest principal stress minus the smallest principal stress. So if sigma 1 and sigma 2 are positive, the smallest is sigma 3, which is 0. Okay? If sigma 1 is positive and sigma 2 is negative, then in reality, sigma 2 is 0 and sigma 3 is negative. So you take sigma 1 minus the negative number, so you get a larger stress. Okay? Well, this is going to become a bit clearer when we solve the exercise, hopefully. Finally, von Mises is the maximum distortion energy. Now, you probably won't remember in the first year, because I know you don't, but I taught you about the shear strain and shear stresses, normal strain, normal stresses. And I said that the normal stresses and normal strains are the ones who change the volume of the structure. Okay? And the shear stress and shear strains are the ones that change the shape of the structure. So the normal stresses are responsible for the change in volume. It's a scaling. Same shape, just scaled up or down. Whereas the shear stresses are responsible for the distortion. So the maximum distortion energy comes from this deviatoric tensor, which we call, which is based just on the shear stresses, and can be summarized in 2D only by this. So the sigma equivalent is the square root of sigma 1 squared minus sigma 1 sigma 2 plus sigma 2 squared. This must be smaller than sigma yield for ductile materials. This is what von Mises is saying. You also have the 3D equivalent of this. I'm sure that Said has taught you that as well. You won't be needing this now. You will be needing this next year when we do stress and dynamic analysis. Okay, last bit of information, safety factor. What is the safety factor? Well, the safety factor is the right-hand side of this equation divided by the left-hand side of this equation. This tells you how much your structure is safe. Okay? So if sigma yield, if the sigma equivalent is exactly the same as the sigma yield, that means you are on the brink of failure. Okay? Because you are using 100% of the stress budget of your structure. So you are exactly on the brink of failure. A tiny bit of stress more and the structure fails. So this one, if the factor of safety is 2, that means that sigma yield is twice as much as sigma equivalent. So you can use twice as much the budget. You are at 50% of the budget of stress used for the structure. So the structure is safe too. That means you can load it up twice as much until it fails. Now, factor of safety for mechanical structures are in the range of 1.8 to 2.5, more or less. Factor of safety for civil structures are 5, 6, 10. So depending on what kind of thing you're using, safety factor is very important. Also, what happens if you have well, safety factor also takes into account everything that you didn't account for in the design. So if you're not sure about something, some effects, new materials that you use or something else, then you want to increase this factor of safety. So you also put the factor of ignorance in your calculations. All right, so let's solve. Now that we know everything, let's solve this very, very, very simple question 5. The shaft shown in figure 5 is subjected simultaneously to a bending moment. So let's say the bending moment is going in this direction. And let's say it's a positive bending moment. And there's also a twisting torque. Are you familiar with the notation of torque with the double arrow? Double arrow means this is the axis around which the torque is rotating. Okay, so like this, like this. Of course, this is a fixed support, so it also reacts with the twisting torque and the bending moment. Okay, so this is positive bending moment, constant, and constant twisting torque all the way across. If I look at the bending moment diagram of this, it looks like this. Positive. If I look at the torque diagram, it's also positive. Okay, positive, everything is constant. So which one is the most stressed section? All of them, because they are all under the same internal loads. Now, on any of these sections, which one is the most stressed point? Well, let's say that this moment, this bending moment is around X. So this bending moment is acting around this axis. Okay, so no, it's the other way around because it's bending up. Okay, it's bending up. So which one is the neutral axis? It's exactly the axis of the bending moment. So this one is also the neutral axis. So if that's the neutral axis, which one is the most stressed point according to the bending moment? Top and bottom. Okay, so you remember that the stress distribution looks like this. Sigma max. So let's put so this is X and Y, so Z goes outside of the axis. So Z is along the axis. So let's call this sigma Z max. And this is, of course, sigma z max. And according to the twisting torque now I can draw like this. Sorry, it's the other way because it's positive. So which one is the most stress point according to the twisting torque? Any point around the boundary. Yeah.
How do you know where the bending moment on the foot at?
Just a second. This is tau max. So for all the points, so for the torque, all these points are the most stressed. For the bending moment, this one and this one are the most stressed. So let's say that we take this point here. Let's call this point A. And this point here, let's call it point B. And we say that these ones are the most stressed points on the section. Can you show this on the infinitesimal? Yes, of course we can. So let's do this on the infinitesimal. Let me move this around. So let's show point A and point B on the infinitesimal. Point A is this one. So point A, of course, if I look at it from the top means this is X and this is Z. Do you agree with me? This tau max, how is what kind of tau max is this? Tau xy, tau xz, tau yz? Do you remember? Remember tau xy, what does it mean? The face of normal x, direction y. So which tau is this? Tau xz. I say almost. It's tau zx. Yeah, which is the same number, but it's not the same thing. Let me check. Xy. No, it's not xy. It's zx because this is x and y. See, this is x and y. So we are on the face z, on the face with normal z. Okay, so the normal of this face is the z axis. So this is tau z, and which direction is this going? In x direction. Okay, so this tau max is tau zx. Okay, which is negative, as you can see, because it's on the face z, but it's opposite to x. So tau zx looks like this. On the z face opposite to x. This is tau zx, and so this one is the other tau, and this one is the other tau, and this one is the other tau. And then we have which other stress? Sigma z. Sigma z is compressive for A. So sigma z goes in the z direction, opposite. So sigma z is this. Agreed? So this is the stress for A, and the stress state for B is, this is still tau zx, but now it's positive, see? So tau zx is positive. If I look at B from the bottom, looking at B from the bottom, I have this is x and this is z. Agreed? From the top, I have Z that goes down. From the bottom, I have Z that goes up. So I'm looking from this side. Okay? And so I have tau Zx positive. And then I have sigma x, which is also positive, sigma z, which is also positive. Because this one here is positive at the bottom. Okay, so that's how they look like on an infinitesimal element. Do you agree? Good. Now, let's find the principal stresses and maximum shear stress at the point of greatest stress. Now, these two are both point of greatest stress. So let's find the largest shear stress and the largest principal stresses, the principal stresses, which are the largest normal stress, and the largest shear stress. So how do you do this? Well, we just apply the equations. Sigma 1, 2 equals sigma x plus sigma y divided by 2 plus or minus square root of sigma x minus sigma y divided by 2 squared plus tau xy squared. See, I don't even need the formula sheet because this thing is easy to remember when you know what these things are. Sigma average plus the radius of the Morse circle. Well, tau xy you can find very easily. So, well, in this case, let's not call this tau xy because it doesn't mean anything. In this case, this is tau zx. Okay? And this is sigma x and sigma z. Because we are in this plane zx. So don't be fooled by the fact that it's sigma x, sigma y, depends on which plane you're looking at. All right, well, you do the calculations. I'll write down how to find tau zx max equals T divided by J times R max. R max is, of course, phi divided by 2. Phi is 40 millimeters here. And the largest bending moment, the largest sigma z max is the bending moment divided by Ix, because we are rotating around x times y max. And y max is also phi divided by 2. Okay, you do these calculations and you find the stress. What's the stress? If you use Newton millimeters, millimeters to the power of 4, and millimeters here, you get an answer in megapascals. Come on, do this calculation for me. Also remind that J is pi phi to the power of 4 divided by 32, and Ix is pi phi to the power of 4 divided by 64. Okay, I won't repeat myself because these are all the same things. Yes? 22.87 for the shear stress.
23.87 for the shear stress. And from max for the other one is 71.62.
71.62. Thank you. And now you can plug these numbers here in here to find sigma 1 and sigma 2. Okay, can you do this calculation for me as well?
That is sigma 1 is 78.85 and sigma 2 is minus 7.2.
Minus 7.2. Okay, thank you. And what's the largest shear stress? This is easy, you just take this. How much is this?
42.
42?
43.
Oh, 43. There you go. Easy. Well, easy once you know this. The hardest part is to draw the infinitesimal, because you have to have very good spatial intelligence. This it's called spatial intelligence. It's not mine. Yes.
So how do you know where, what thing the bending moment and the shorter axis?
Okay. So what I'm saying is that this is bending up and down. Okay. This is bending up. So bending up means bending around the x-axis. Do you agree?
How do you know this?
No, it doesn't say. It says it's under a bending moment. So I don't know which plane it's bending. So I'm saying it's bending up and down because it doesn't matter. Okay, it's just since it's a circle, even if you rotate the bending moment, it just changes which point is the most stressed, but it doesn't change how. Okay. Yes.
Could you go over, you know, we've got planes A and B.
Yes.
I got a little bit lost of what planes they were.
You mean this and this?
Yeah.
Okay, so the plane, I'm looking at A from the top. So if I look at this from the top, okay, I have that the y-axis is coming out, okay, the x-axis is going right, and the z-axis is going in this direction. Okay?
So in this case, you're saying Y, that's Y, and so here's the pole, that's
Yeah.
that's Y,
Yeah.
that's X, and that's Z.
Yes.
Okay.
And you're looking from the top. And now you see why it's very important to rotate the infinitesimal elements, because if you look from the top, but then you rotate 90 degrees, you're looking at a different element. Okay? Although the element is different, the results are the same. Sigma 1, sigma 2, and tau max are always the same. And that's what's important. Okay, now that we have, see, this is not the end of the story, because now that we have sigma 1 and sigma 2, we can choose any failure criterion, any of these, and find the factor of safety. And then we can verify if the structure is safe or not. There are two main ways of doing these structural analysis. One is verification, which is knowing the loads, find the safety factor, which is what we are doing now. There is design. Design is, given the safety factor and given the material, find the dimensions that are required to sustain a certain load. Okay, so you start from the back. At that point, you start from the safety factor. You find sigma 1 and sigma 2, and then you find sigma x. You find which one is the most stress point, and then on those stresses contain, as you can see here, contain the diameter. And so your unknown is inside this large equation, and then you can find it's a large equation in a single unknown that you can solve with MATLAB, or if it's easy enough, you can solve it by hand. Okay, good, good. Okay, question 3.
Arnaldo, there's a question in the chat box.
There's a question in the chat box. Sorry, let me check the chat. Why is M going left? Okay, where M is going left because I'm just saying that this is bending up. So in order for this to be bending up, it must be bending around this axis. So if you put your thumb along the axis of the moment, so along this axis, then you see that this rotation is bending everything up. So this arrow is coming out of B, and this arrow is going into A, so that this is bending. Is this clear? Yes, very good. All right, so let's do question 3. I mean, this is very, 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 very easy. So a plane element is subjected to stress indicated below. What are the principal stresses and their directions? And what are the maximum shear stress and their directions? We are only doing part A. This one I will solve using Moore's circle, because calculations are very easy. You just use this equation again and these ones to find the directions, and that's it. Okay, so let's use the Morse circle to solve this one. I put here also, very nice, one of my slides for the derivation of the Morse circle. Remember the equations we used last time for sigma x prime and sigma y prime? If you take those, you square them, you sum them up, you end up with this equation here that you can rearrange again as sigma x prime minus the average sigma plus tau xy equals this thing, which is just a number, and that number is the radius squared. So this is the equation of a circle, and that's how Morse came about the circle itself. Okay, so x minus x0, so the center is at sigma average. Y0 is 0, so it's always, the center is always lies on the sigma axis. And this one, this beast here, is the radius of the circle. The radius squared, so the radius of the circle is this thing. Very, very, very easy, very convenient. You learn this, you don't need to remember the equations because they come out automatically. All right, so let's draw the infinitesimal A. The infinitesimal A looks like this. And we have x and y, so let's say that x is in this direction. Let's use the classic reference system. And the y-axis is in this direction. So I have sigma x is 100 megapascals, which of course go like this. Sigma y is 0, so I don't draw anything. And tau xy is 25. So tau xy is on the x phase direction y. So this one. And of course, if this is like that, you have one like this, and then you have one like this, and one like this. This is the infinitesimal A. Now, let's use the Morse circle to find the stress, the principal stresses and the shear stresses. This is the Morse, these are the axes, the sigma axis and the tau axis. Remember, this is the counterclockwise, this is the clockwise direction. And so you have that. How you draw the Morse circle? Step 1, find what? Well, step 1, draw the axis. Step 2, find what? Coordinates. Which ones?
Sigma 1 and
Sigma x and tau xy.
Yeah.
So sigma x is 100. So let's say that this is each one of these is 25. So I'm saying that this thing, 2, 3, 4, and say that this is 100 megapascal. Okay, so this is my units. So 25, 25, 25, 25. This is 100. And then I have 25 positive, so it's here. So point A is here. Agreed? Point B is at 0 minus 25. So point B is here. Sorry, here. Agreed? And so I can just draw the Morse circle. This is the thing. So I see that the average stress is 50. It makes sense. 100 plus 0 divided by 2, it's 50. See, it's exactly halfway through. This is my sigma average, 50. And now I draw the circle. The circle must pass from B and A and must have 50 as its center. There you go. There you go. So how much is sigma 1? Sigma 1 is this point here. This one is sigma 1. This one is, of course, sigma 2. As you can see, sigma 2 is negative. It's very tiny, but negative. And I believe it's 12.5, minus 12.5. Because this, so sorry, this one is 25. So this is 25 divided by 4. How much is that? Yeah, 6 and 75. No problem. Let me check. Minus 6. There you go. Minus 6. Nice. And let's check how much is sigma 1. It's 100, and this is 25. Yeah, so it probably is 106-ish. Yeah, 106. See? It works. It works. And it works wonders. How much is tau max? So this is about 106, and this is about minus 6. Let's check how much is tau max. Well, the tau max is 25, 50, 56, more or less. Yeah, plus or minus 56. And it's plus or minus because it's tau max here, but it's tau max also here. It's tau max in both directions. One is clockwise, which is negative, and one is counterclockwise, which is positive. These both are about 56. Minus 56. How easy is this? Very easy. How fun is this? Very fun. Can we find the angles as well? Yes, we can. Yes, we can. So this is 2 theta s, which of course I can't measure here on this paper, but if you add a protractor, it's very easy to measure. And this one here is 2 theta p. So you can calculate them very easily using the equations. These are the equations to calculate 2 theta p and 2 theta s. Or you can find them out by just measuring them. That's it. That's it. Very easy. So try to do this. It's probably used. My scale was very bad. I'll probably redraw this on a larger scale. Let me see if I can increase this. There you go. Much nicer. All right, Lynn, is there any other question that we need to solve this one? Well, question 4, it's just more of the same. Okay, so let me do this very quickly. And then I'll give you a break, and then we can solve the other questions. So I'll just use, so I use the Moore's circle. So ARM uses Moore. You do analytical. Okay, so I use the fun method, and you use the boring method. By the way, the fun method is what you will be asked at the exam. Okay, so make sure you know how to draw these things, and especially you learn the theory, because at the exam you also have theory questions. So this is 50. So let's say that this is X and this is Y. So I have that X is negative and Y is positive. So sigma x is minus 30. So 10, 20, 30. Sigma x. 50. Positive 50 sigma 1. Sorry, 1, 2, 3, 4, 5. So this is 50 sigma y. And then I have tau xy is negative 40. So tau xy is negative 40. So it's 1, 2, 3, 4. So the intercept between sigma x and tau xy is point A. And the intercept between this and exactly the same on the other side. So of course you also have 40 on this side, which is 10, 20, 30, 40. This is tau yx. And the intercept of this and this is point B. So I just join them up with a straight line. And lo and behold, they meet at 10 megapascal, which is the average stress. Is 1, 2, 3, sigma x. Yeah, minus 30 plus 50 is 20, divided by 2 is 10. So this 10 is sigma average, which is where the center is. And now I can draw the circle. That's an ellipse. Come on. There you go. So the center is here. Must pass through A and B. The center is here and must pass. There you go. Nice. I am stunned. Very nice. And so I can find very easily, again, I can find sigma 1, sigma 2, this line, which indicates 2 theta p, and this line, which of course passing through the center, very important. That indicates 2 theta s and tau max and tau min. So the other tau max, sorry. Okay, very fun. I love it. No, I didn't put numbers, but it's very easy to see that if this is 50, 50, 60, 50, 60, 65, 67, more or less. Sigma 1 is about 67. Sigma 2 is minus 30, minus 40, 45, minus 47, minus 46, I would say. And tau max is 10, 20, 30, 40, 50, 51, and minus 51. Let me check. Sigma 1, 66.6, I said 67. Sigma 2, minus 46.6, I said minus 46. Tau max is not required, so, but I also found tau max. See, very nice. Very easy, very fun. Let's have 10 minutes break. Okay, let's make 8 minutes break. So I'll see you later. If you have any questions, I'm here.
Another.
Yes, Lynn.
If you look at the solution in the solution sheet, in the Q48, you see the x is minus 30 plus 40. I mean, it should be minus 30, minus 40.
It should be minus 4, but in this case it doesn't matter because it's symmetrical about the sigma axis, so it's just the same solution flipped.
Okay, yeah, okay.
I mean, it's a mistake, but it doesn't matter in this case in terms of numbers.
Yeah, I mean, if you see his graphic, the tau is to the upward, right? In your graphic, tau is downwards. I mean, the direction of tau.
Yeah.
But they are the same, right? I mean, when we draw the circle, they're the same.
Okay, while we wait, I'll also draw this infinitesimal. Yeah.
Another, you're right.
Yeah. How's it going?
Question.
Of course. Let me just finish this up. 67 and minus 46. There we go. Yeah.
Cool. Basically, so I get this, I get that, and I get this section here. That's a bit of revision on that, anyway. I don't get how to go from here to here. Basically. This section confuses me. It just confuses
So let's have a look. Can I?
Yeah. I'll bring the pen over.
No, it's fine. I'll point it out like this. So that's your issue. Your issue is that. So what is X? Is it belonging to this or this? Okay, so that's your issue because I used a different one. I used a different reference system. My reference system was that X is this.
X is sorry.
This one of the section.
X the one
so this axis here is the Z axis for me. This axis here is the Z axis.
Okay.
This is the Z axis.
Okay, I'll follow you. Yeah.
I mean, it's fine. You just have to change to shuffle things around. That's the idea. Okay?
Yeah.
Okay. It's not wrong.
But then the thing is, how do you go from here? Where do you get your stresses from?
What do you mean with stresses?
How do you get sigma X and sigma Z? That's
because you are in the XZ plane. So you must use X and Z.
Oh no! But where did you get the values? How do you find the values?
Here.
Okay.
So you have drawn these, and these are exactly the stress that you're using. Sigma Z. Yeah.
That makes sense. I was going to ask you if I found it.
Okay, so this one, sigma Z max, is this.
Right. I'm slowly getting.
Which is what we did
I'm slowly getting.
in the last 2 weeks.
Because I got a little lost, and that's why I said I need to literally circle that. So I need to revise it.
Yeah, exactly. So you need to remember these things that we did 2 weeks ago.
I is the second moment of area, and J is the second moment of shading.
It's the polar moment.
Polar moment. Okay.
What is phi symbol mean?
Well, it's phi. It just says that the diameter is phi.
Oh, the diameter is phi. That makes sense.
That should be D.
And that's in meters, right?
Cheers.
Yeah,
Right.
it's millimeters. Yes.
So could you like explain this section of question 5? I don't know.
This one?
Yeah, like
Okay.
just like the A's and B's. I don't really get what's going on there.
So this is this A. This is not A. This is the neutral axis.
Oh,
Just
okay.
this goes here.
Oh yeah, I know about
So what I'm saying is that the since I said that the moment is in this direction, so the arrows come out of B, this arrow goes into A. Okay. So the largest stress is felt at B and A for the bending moment.
Okay.
Now, for the twisting torque, the largest shear stress is everywhere around this.
yeah.
So which one are the most stressed point? For the torque, any one of these is fine. For the bending moment, it's either this or this. So in total, it's either this or this. Okay. And then I've drawn both. This and this.
Alright, so this is the is that normal stress?
Yes. So this one, this should really be like this.
Yeah.
So this arrow should be coming out of B and into A. Of course, I can't draw it like this. In reality, it should be this should be perpendicular.
Yeah. How do you also determine the moment? Are you doing this?
You use your right hand, put the thumb along the axis,
On the axis.
so it's bending in this way.
Okay.
So it's bending up.
All right.
With this bending up. For analytical method, which equations are used to find the theta values? These ones. This one for the principal directions, and this one for the maximum shear direction, which is just equal and opposite. So this is just the opposite of this with a minus sign in front. This will explain the right-hand rule. What do you mean? This. So ideally, what you want to find is, so this double arrow notation. This double arrow notation indicates around which axis the moment is applied. So this is around the x-axis. So if you put your thumb, use your right hand. If you put your thumb along this axis, and then you rotate your hand, this will be the sense of rotation, the sense of bending of this structure here. So if you imagine that the structure comes out, you put the thumb along the axis, and this bends like this. And this bends like this. Okay, so this is the thumb, so it bends in this direction. Guys, I think that the best way is practice. If you practice, you're gonna ace the exam very easily. Because all of this spatial intelligence comes from experience. That's the only thing which is required to train this spatial intelligence I was talking about.
Yeah.
Yeah.
You know the people who spoke, I mean the rotation course on Tuesday Friday.
Second?
You know the course on Tuesday Friday. Can it be? Do you have like an extra day for it? Is it like the grace period?
It's yes, it's 24 hours. So it's not an extension.
So you just have. It's better to submit before.
Yes.
But if you submit afterwards, that's still right.
Yes, but don't use it for as a last attempt of catching a straw. Okay, so that's useful if the server is overloaded and it doesn't let you submit because the server times out because everyone is submitting at the same time. Okay? So sometimes the uploading fails, and so we give you this grace period just to avoid these things, because otherwise, okay, I couldn't submit because the internet was down or the server has crashed, and then you won't be getting zero. Okay.
I think it's gonna be me, so we
Can you please input the values for theta in question 4? You're not getting 22.5. So this is sigma x. This is sigma y. And this is tau xy. Guys, can I please ask you to run this calculation for me? So can you find theta p for question 4a? Are you getting this number or not? You're getting minus 67 point. So minus 67.5 is this one. Okay. Now, of course, you have two angles. So this, no, this is sigma 1, sigma 2. So minus 67.5 is this one. But you have two angles. You can rotate this in one direction, or you can rotate this in the other direction. Agreed? So if you find, so the principal directions are two directions always. Theta p1 and theta p2. Theta p1 is the shortest rotation. Theta p2 is the largest rotation. Sometimes you find the shortest one, sometimes you find the largest one. As you can see, the sum of these two is 180 degrees. Divided by 2, which is what you're looking at, is 90 degrees. So once you find 61, how much did you say was 67?
minus 67.5.
So minus 67.5. If you add minus 22.5, you get minus 90 degrees. Okay, so you're just finding the complementary angle. So don't be scared. If you don't find exactly the same, it's because you're finding the complementary one. So it doesn't matter. So Asia, is that okay? Does that answer your question? Yes, great. So you also got 67 point something, I believe. All right. So again, don't be scared. Everything is normal. Also for theta s, it's the same thing. You can go in this direction, which is the shortest one, but you can also go in this direction. And these also make 180 degrees, which is 90 degrees because divided by 2. And so if you find theta s1, you can always find theta s2 by taking the complementary angle. All right, let's do question 8. Link, which one is the question that we answered? 8 or 6? I think it's question 6. Yeah, let's do question 6. And then question 8. Question 6 is very easy. Now, the direct stresses acting on an element in directions at right angles to each other are 60 megapascal tensile and 45 compressive. Now, it doesn't say which one is sigma x, which one is sigma y. So let's make up our own mind. So I'm saying this is the infinitesimal. This is the x-axis. This is the y-axis. And so it says that sigma x is 60 megapascal tensile. And sigma y is 45 compressive. Tau xy is 37.5. It doesn't say anything about being positive or negative, so let's say it's positive. 37.5. We also know that the yield stress of the material is 240 megapascal. So let me say here that the yield stress is 240 megapascal. So let's find the safety factor according to these three different crisis functions. So maximum principal stress, maximum shear stress, maximum shear strain energy. So these are just Rankine stress conformises. So what do we need? Well, we need the formulae. So I'll just copy and paste here. And all these sigma equivalent can be found by knowing the principal stresses. So let's have a look at the principal stresses. Now, can you please find the principal stresses of these? I can do this on a Morse circle, but this will take too much space. So can you please let me know, do this calculation very quickly to find sigma 1, sigma 2. So first of all, calculate sigma 1, sigma 2 principal stresses. How much is sigma 1? Come on. As you must run the calculations at the exam, okay? So don't take too much time. Practice your calculator full. Come on, online chat, anyone? How much is sigma 1? How much is sigma 2? So let me recap here that sigma x is 60, sigma y is minus 45, and tau xy is 37.5. 90.7 with a question mark. So, okay. This is sigma 1, I suppose. Did you get 90.7? Yeah? No? Anyone? Come on. Did you get 90.7? Come on. So he got 72.0 and minus 57.0, you said. So is this correct? 72 and minus 57? Guys, it's not an action. It's should be the same number for everyone. Do you agree? So it's 72 and minus 57. Okay. Marius, please re-look at your calculations. Okay. So sigma 1 is 72. Sigma 2 is minus 57. How much is sigma 3? Well, the other sigma is 0. So we are saying that this is really sigma 3. Okay? They are always in order. Sigma 1 is greater than sigma 2, which is greater than sigma 3. Okay? 1 is 0 because we are on plane state stress. So one of these sigma is 0. The largest one is 72. The smallest one is minus 57. And so that means that, let me put this in the other order. So sigma 3 is always smaller than sigma 2, which is always smaller than sigma 1. So this one is sigma 3. This one, sigma 2 is 0. And sigma 1 is this. Okay? Now these ones are really useful just for Tresca. These ones are the same. So let's solve the maximum Rankine theory. So A for A, we have that sigma equivalent. How much is sigma equivalent? Is the largest between sigma 1, sigma 2, and sigma 3. Which one is the largest? Sigma 1. It's the absolute value. So if sigma 2 or sigma 3 were minus 83, say, that would be the largest one because it's an absolute value. So sigma equivalent in this case is 72. Yes?
How did you, sorry, where did you get sigma 3? As in,
It's so one of them is 0. Sigma 1, sigma 2, sigma 3. We are in plane stress. Plane stress means that one of them is 0. Now, the largest one is always sigma 1. The smallest one is always sigma 3. And then the middle one is always sigma 2. Now, in this case, 72, 0, and minus 57, you can rank them by saying that 72 is the largest one, 0 is the intermediate one, and minus 57 is the third one.
how do you know sigma 2 is 0?
Because 0 is always there. Because we are in plane stress. In plane stress means that one of the sigmas is always 0. Next year, when you do 3D stresses, then you can actually rank them because all of them are different. Okay? So for Rankine, sigma equivalent is 72. So what's the factor of safety? For Rankine, it's sigma yield divided by sigma equivalent, which in this case is 240 divided by 72. How much is that? 3.3. What are the units of the safety factor? No units, because it's a stress over a stress. Sorry, you can't see it. Yes, I see it's sigma 3 because it's the, you can rank them algebraically. So a negative number is always smaller than 0. So let's have B, Tresca. And that's why it's very important that we identify sigma 1 and sigma 3, because Tresca says is always the largest one minus the smallest one. So the sigma equivalent for Tresca is 72 minus 57. Largest one minus the smallest one. Agreed? So how much is this? It's 129. And so the factor of safety, according to Tresca, is sigma yield divided by the sigma equivalent, which is 240 divided by 129 is 1.86. Thank you. And finally, this is von Mises. Sigma equivalent is the square root of sigma 1 squared minus sigma 1 sigma 2 plus sigma 2 squared. I know this by heart. And again, this is always the case, even if you have sigma 3. Okay, so let's call this sigma 3, because sigma 2 is 0. I mean, if you use the 3D equation for Tresca and 1 is 0, you always back up this one. Try and experiment with the formula. How much is that? $110? 12? Is that it? 112?
Yeah.
No point anything. Okay, 112. So the factor of safety, according to von Mises, is sigma yield divided by sigma equivalent, 240 divided by 112. How much is this? 2.14. Now, question. Which one of these criteria is the most conservative? Yes, because it gives you the smallest safety factor. Okay? You always want to design things to be the most conservative possible. Now, von Mises is more adherent to the reality, but Tresca is more conservative. So if you want to be a good engineer, you use the most conservative one. If you want to be an engineer that saves money, you use von Mises. If you are a bad engineer, you use Rankin. Okay? Because this is a yielding material. You have sigma yield, so you should not be using Rankin anyway. Okay? Because this is wrong. This is a conceptually wrong thing. This will make you lose many marks at the exam if you use this. Because this material is ductile. How do I know it's a ductile material? For the simple fact that we have yielding. This is a ductile material. And so that means we can't use this. This only applies brittle materials. Okay, now if you are a chartered engineer and you are summoned from a court that has to check the responsibility for the design of a structure that has failed and has killed some people, okay? You will be redoing the calculation that the designer had done. Okay, so if you do these calculations and you find that the safety factor is 1.1, according to Tresca, and it's 1.3, say, or 1.4, according to von Mises. Now, the design specification said that the allowable factor of safety would be 1.3. So the design is up to specification for von Mises, but it's outside specification if you use Tresca. Would you say that the engineer, the designer, is at fault or not? Is it guilty or not? Should he get jail time or not? Should he be convicted? What do you think? This is very important. This is how engineering, one day, it would be your responsibility to send someone in jail or not. Okay. So what would you say? It's complicated, okay? It's complicated because I'm sure it's not just the designer responsibility on that case. It's not only the designer responsibility, it's most certainly the company responsibility that must have used the correct. Also, it's very, very narrow. It almost never happens that you are in this range for which one is safe and one is not. Okay? But generally, if one is safe and one is not, you always go on the conservative side and say, okay, let's make the Tresca criterion safe. Okay, second? Yeah, of course. If you are the designer and you put your signature, you are responsible for what happens. That's why they cover you with money, because with money comes responsibility. Okay, they just don't give you money for that. If you are an engineer, of course, if you work for a company, then you are not responsible, the company is responsible. Okay? If you're an engineer working by yourselves as a chartered engineer, registered, it's your own sole responsibility. Now, of course, if you are responsible in a company, then the company is responsible, but then the company will probably fire you. Okay? That's the idea, because yes, the company is responsible, but you did the mistake, so you are liable for the mistake. I can't send you to jail, but I can fire you. All right. Any questions? No? No questions? So let's do question 8. Now we have Moore's modified shear stress theory. I don't think you've done this, and if you've done this, there is, of course, crisis function that take into account maximum shear stress, maximum principal stress, all combined, and you also have that some materials like stone has very, very strong resistance to compression, but it's very brittle in tension. So when you're designing stone structures or cement structures, all these kind of materials have different resistances in compression and tension. So you need modified failure criterion. In that case, more modified shear stress theory is one of those. I don't think you've done this, and if you've done this, it's you need to use tables. It's a bit more complicated than these ones that we just used, but it's just a different crisis function. Still take into account all these three numbers and spit out another number. The only thing that's different is that this number is a function of the stress, of the direct stress that is under consideration. Now let's do part B. A solid steel shaft transmits 3 kilowatts of power when rotated at 1500 RPM. There is an axial thrust acting on the shaft, which produces a compressive stress of 2/3 the magnitude of the shear stress. Okay. Determine the required diameter. So this is a design question. See, you need to determine the diameter of the shaft that can do this task without failure. And also, you want you know that the allowable shear stress. So the material is given, and okay. So it doesn't say the factor of safety. So we will assume the factor of safety 1, which means it's the shaft that can barely manage this without failing. Okay? If you want to be more consistent, well, a real design, you would take a factor of safety of 2.2, say, more or less. So you can account for dynamic loading and all these other things that you have not accounted for, imperfections, and all these things. So remind me, please, what is the equation of power? Rate, yes, rate of work is the torque times the angular velocity. Torque is in Newton meters. Angular velocity is in radians per second. And this gives watts. Newton times meters per second is power, which is energy over time. All right, how much is T? Because that's what we want to find. We have power, we have angular speed, we want to find T. So how much is T? It's not 2, because you have to convert 1500 RPM into radians per second. So how much is T? Online students as well, please help me out. It's 3000 divided by 1500 converted into radians per second. It's 1500 times 2 pi divided by 60. So this is 3000 divided by 1500 times 2 pi divided by 60. How much is this? $19.1 Newton meters. Agreed? Agreed. Okay, now that we know this, we can also find the shear stress. How much is the shear stress? Tau max is T divided by J times the diameter of the shaft divided by 2. Agreed? Times the largest possible radius, which is the circumference. Now, since the diameter is unknown, let's explicitate this into T divided by pi d to the power of 4 divided by 32. So this is 32T times this, agreed? Times d divided by 2. So this is, again, this go away, and this go away. This is 16T divided by pi d cubed. Agreed? And that's it. Because this is a number, T is a number, but D is unknown. And that's one of the issues with the design pathway, is that this unknown, you have to bring it forward with you in all the equations. So that's tau max, but we also have sigma. Remember sigma? How much is sigma? It says here that we have an axial thrust produces a compressive stress of 2/3 the magnitude of the shear stress. So the magnitude of the shear stress is this, which we don't know because D is unknown. But we know that sigma max is negative 2/3 of 16T divided by pi d cubed. Agreed? And so I can also say that this is 32 divided by 3, and let's do this. It's minus 32 divided by 3 T pi d cubed. Okay, now, according to von Mises, let's also say that sigma yield is 150 megapascal. And now we need von Mises. But von Mises, sigma equivalent is, so sigma equivalent von Mises is square root of sigma 1 squared minus sigma 1 sigma 2 plus sigma 2 squared. What is sigma 1? Well, sigma 1 comes from these. Ouch. So sigma 1 comma sigma 2 equals sigma max. This is sigma x, say. I don't care if it's x or y. X on y. Y is 0. Sigma max minus 0 divided by 2. Sorry, plus 0 divided by 2 plus or minus the square root of sigma max divided by 2 squared plus tau max squared. Agreed? And now these things are all these beasts that we just found. So I can say this sigma 1, 2 is, this divided by 2 is minus 16 divided by 3 T pi d cubed plus or minus the square root of 16 divided by 3 t squared plus 16 t divided by pi d cubed squared. So let's do this. This one becomes 16 divided by 3 squared, t squared, pi squared, d to the power of 6, plus 16 squared, t squared, pi squared, d to the power of 6. And so this one can be rearranged as 16 divided by 3 squared plus 16 squared so this as a subject times t squared pi squared d to the power of 6. Agreed? Yes or no? And so this becomes the square root of 16 squared divided by 3 squared plus 16 squared times t pi d cubed. Do you agree with me? So how much is this number? Can you give me how much is this number? Very important. $28.4. So let's say 284 divided by 10. So in the end, this thing becomes 284 divided by 10 t pi d cubed. Agreed? And we want to add minus 16.3. So sigma 1, so let me take this out. Don't need this anymore. I was just doing some algebra. So sigma 1 is 284 divided by 10 minus 16 divided by 3 t pi d cubed. Sigma 2 is minus 284 divided by 10 minus 16 divided by 3 t pi d cubed. Agreed? How much is this number? How much is this?
Minus 506 over 15.
Okay. Can you please check this number again?
This number,
I see. Did you gave me 28.4? Was that number or the square root of that number? So let's ask Wolfram Alpha. Say again, how much is that? So I want square root of 16 divided by 3 squared plus 16 squared. Oh, sorry, this is 16 divided by 3 all squared. Uh, 16 square root of 10 divided by 3. Okay? Which is probably, it's 16.86. Okay, so let's use this. And 16 divided by 3 is 5.333. So this one is 5.33. And so I can say very easily that this one is 16.86 minus 5.33. And this one is minus 16.86 minus 5.33. So this one is 16.86 plus, sorry, minus 16 divided by 3. It's 11.526, 11.53. T divided by pi d cubed. And the other one is this minus that. So this, minus 22.19. See, design is messier. So you have all these numbers popping up. But it's also funnier, I believe. So now that we have this, we have to still apply sigma equivalent for Mises. Okay? So sigma equivalent for Mises is equal to, and again, this T pi, this, so this is just 11.53 squared minus sigma 1, sigma 2, which is 11.53 times 22.19 plus 22.19 squared. (29.68). This is 29.68 t over pi d cubed. Okay. Good, good. So this one is sigma equivalent, but for a safety factor of 1, so factor of safety, let me put it here. Where do I place this? Factor of safety is 1, but factor of safety is also equal to sigma yield over sigma equivalent. So that means that sigma yield is sigma equivalent. And so that means that this is also equal to sigma yield, which is 150. Okay? So you solve this equation here. Solve the equation 29.68 times t divided by pi d cubed equals 150. The only unknown here, t is given. Remember, t is 19.1. The only unknown is d. Problem is, we have used millimeters everywhere, so make sure that t is in Newton millimeters. Okay, because everything we used megapascal, so this one we should really be using 19,100 Newton millimeters. And you'll get your diameter in millimeters. So this one gives d is the cubic root of 29.68 divided by 150 times pi divided by t. Agreed? So this is the smallest possible diameter that make this power transmission at this torque, this speed, and this power possible. How great is this? This is your very first design attempt to a machine. Now, when you go to your workshop, say at home you have a workshop and you say, oh, I already am an engineer because when I was a kid, I designed a shaft that was transmitting power. Yes, but that's not design. That's trial and error. Okay, because you do it, you use a larger and larger shaft until it doesn't fail anymore. Now you know exactly what is the diameter that separates failure from success. And then you try to enlarge your safety factor to skew it more towards this success, of course. That's the idea. Any questions? No? I think that's fun. Now, this last one, I don't want to solve, but I want to show you how it works. You have a cylindrical steel pressure vessel with an inside diameter of 2 meters, it's a very large one, and a wall thickness of 1 centimeter only. It's one large and thin pressure vessel. What is the maximum safe working pressure for this cylinder if the yield stress is 350 megapascal and you want to use a factor of safety of 3.5? Design this using Tresca and using von Mises. Now, see, what happens now is that we have used von Mises here to back up this diameter. If you used Tresca, which gives you a smaller, which is more conservative, you would have gotten a larger diameter. Okay? So Tresca is more conservative and therefore uses more material. And therefore it's more expensive. Okay, so that's what I was saying earlier. If you are an engineer that wants to save some money, use von Mises because it allows smaller shafts, so use less material. And so generally it costs less. So how do you approach this one? Well, this one is very easy. You have done cylindrical vessels, pressure vessels, and you know that pressure vessels are always in a principal stress state. You don't have to rotate anything. Pressure vessels are already in a principal stress state. So if you find sigma hoop, it's already sigma 1, and sigma axial is already sigma 2. So in this case, it's very easy. You don't have to rotate anything. You don't have to find the principal stresses. They're already there. P is the internal pressure. R is the radius of the inner face of the container. And T is the thickness. And why sigma 1 is this and sigma 2 is this? Well, because this one is always double as much as this. This is half as much as this. So this sigma 1 is always the largest one. So sigma hoop is always sigma 1, and sigma axial is always sigma 2. Again, knowing this, you can apply Tresca very easily, sigma 1 minus sigma 2. And so let me write the equation here. The safety factor for Tresca is sigma yield divided by sigma 1 minus sigma 2. And the safety factor for von Mises is sigma yield divided by square root of sigma 1 squared minus sigma 1 sigma 2 plus sigma 2 squared. And again, this is known. This is known. Inside here, there's the pressure that is unknown. And you can solve for the pressure because you want to find what is the maximum safe working pressure. So this P is the unknown. Okay, so let me explicitate this one at least. This one is sigma yield divided by PR divided by T minus PR divided by 2T. Very easy. So this is sigma yield divided by PR divided by T, 2T, sorry. And so that means that P is factor of safety, Tresca, divided by sigma yield times the radius, yes, and divided by 2T. There you go. this one is already the answer. See how easy is this? Factor of safety is 3.5. Sigma yield is 350. The radius is given, it's 1 meter. And the thickness is given, it's 10 millimeters. You do exactly the same for this, which of course is more complicated because you have the square root, but it's not too much more complicated. Any questions online? Doesn't look like so. So, Lynn, thank you very much for attending. I'm going to stop recording right now.